Good morning, children. Today we will discuss periodic classification of elements. First of all, we should understand what will be the learning outcomes. After studying this chapter, you will understand what is the need of classification. You will be able to explain the early efforts made by the scientists, Doberina triads, Newland's law of octave. You will study about Mendeleev's periodic table. You will be able to explain Mendeleev's periodic law and as well as the characteristics of Mendeleev's periodic table. You will be able to explain modern periodic table and what is the variation of properties across the period and down in the group. So let us start with the chapter. So first, what is the need of classification? Earlier, only few elements were known to the scientists, so it was easy for them to study the properties of those elements. But later on, more and more elements were discovered. So it became difficult for the scientists to study the properties. So they tried to classify the elements. The first classification was done by Lavoisier. He just divided all known elements into matters and non-matters. At that time, in 19th century, scientists knew elements can be classified on the basis of similarity in physical and chemical properties. The next classification was done by Doberina. The classification is known as triad. He just simply made the groups of 3 elements which had similar chemical properties, and this group he called the triad. Then he arranged the elements of the triad in the increasing order of their atomic masses. He observed a trend there. He saw that the atomic masses of first and third elements, if the average was taken, then that was equal to the atomic mass of the middle one. So on the basis of this, he gave the law which we call the Doberina triads. The atomic mass of the middle one is the average mean of the first and third elements. So here just the known elements, he could make only 3 triads. All of you can see the triad chlorine, bromine, iodine. He made the triad, and you saw that the average mean of chlorine and iodine was equal to bromine. Same way, lithium, sodium and potassium. This was another triad, and the atomic mass of sodium was equal to the average mean of lithium and potassium. The drawback of this classification was he could not classify all the known elements into triads, so he could make only 3 triads. So this classification was rejected. Another effort was made by Newland. This classification is known as Newland's octave. He just observed if elements are arranged in the increasing order of their atomic masses, so there is a type of periodicity in the properties of the element. The properties of every 8th element is similar to the first one. Just like the musical octave, as we know that the first note is same as the 8th note. So that is why he called this classification the octave. Here we can see here, if lithium is the first element, then we start with lithium, then beryllium, boron, carbon, nitrogen, oxygen, fluorine. Then the 8th element is sodium. The properties of sodium were found to be similar, same as lithium. Same way, if we start with beryllium, the 8th element will be magnesium, and the two were found to have the similar chemical properties. Now, what were the limitations? This law of octave was applicable only for the lighter elements till calcium only. After calcium, every 8th element didn't have the properties similar to the first one. Moreover, at that time only 56 elements were known, and he assumed only there are 56 elements in the nature. He didn't leave any space for the elements to be discovered. One more drawback was there. He placed nickel, cobalt away from iron, which have similar chemical properties, and the elements which had dissimilar properties, they were kept together. So because of all these drawbacks, this classification was also not followed. The important contribution was made by Mendeleev. So he laid actually the foundation, did the remarkable work in the field of classification of elements. At the time, 63 elements were known. What he did, he took 2 criteria into consideration. He grouped all the elements which had similar chemical properties together, and which all chemical properties he took into consideration? The formula of hydride and oxide made by the elements. He grouped them together, and while grouping them together, another criterion which he used was that he just arranged the elements in the increasing order of atomic masses. Actually what he did, he took 63 cards and wrote the formula of hydride and oxides of those elements on them, and then he arranged them in such a way all the elements which made the hydride and oxide of similar formulae, he kept them together in the increasing order. And when he did this, he just was left with a chart which we call the Mendeleev's periodic table. This is the Mendeleev periodic table. So we can see that all the elements which are forming the same hydride and the oxide, they are together in a vertical column which he called the period, and the rows, vertical columns are called the groups, and the horizontal rows are called the period. So here in this, there were actually 8 vertical columns which he called the groups, and first seven groups, all of you can see, first 7 groups, they were divided into 2. So there were 2 subgroups, but the 8th group was divided into 3. And in this group, transition elements were placed. Then there were 7 horizontal rows of period. Now, on the basis of this, when elements are arranged, what did he see when he arranged the elements on the basis of the similarity in the chemical properties and also arranged them in the increasing order of their atomic masses? Then he saw that there is periodicity in the properties, but it was not after every 8th element. He just simply used the phrase at regular interval. So on the basis of this, he stated a periodic law which we call Mendeleev's periodic law, that says properties of elements are the periodic function of their atomic masses. Means if elements are arranged in the increasing order of their atomic masses, then the elements with the similar chemical properties occur after a regular interval. Then there were certain a number of merits in Mendeleev's classification. First of all, he left some gaps in his periodic table, and he just simply stated, he predicted, these are the spaces for the elements which are not known to us now, but they'll be discovered later. And on the basis of the elements of the group, he stated their properties also. And later on, these elements were discovered. Scandium, gallium, they were discovered later, and they were found to have the properties which were predicted by Mendeleev. So this, the discovery of these elements, and those were found to have the properties which were predicted, they actually just contributed a lot, and the scientists at that time just then accepted the classification of given by Mendeleev. Another merit was it gave a systematic study of elements. The elements which are placed in the same vertical column, that is in the same group, they had similar chemical properties, and which were placed in the different groups, they had dissimilar chemical properties. Moreover, there was a gradual change in the chemical properties when we move from one element to other in the same horizontal. So this provided a systematic study of elements. Then he also corrected the atomic number of some elements like beryllium, gold and platinum based on their properties and the position in the periodic table. These are some merits. There were some limitations in Mendeleev's periodic table. First one, the major limitation was the position of hydrogen was not certain. It could be placed in the first column with alkali metal because it has same electronic configuration, has one valence electron, and other one is it also just has similarity with the halogens. forming the diatomic molecules like chlorine, bromine and iodine. And with alkali metal, the formula of its chloride oxide was same as the alkali metal. So it could be placed with alkali metal as well as with halogen. So there was uncertainty in the position of hydrogen. Another one was, though this periodic table was based on increasing atomic masses of the elements, but there were certain elements which were placed in the wrong order of the atomic masses, as this was cobalt and nickel with high atomic mass, cobalt with high atomic mass was placed before nickel. Same with tellurium and iodine, they were not in the correct order of their atomic masses. This was another limitation. Then isotopes was a major challenge to Mendel's classification. Isotopes were not known at that time, but when they were discovered, they have the same atomic number, but they have same atomic number but the different atomic masses. So according to this, the isotopes of the same element should be placed in the different slots, but there was no space for the isotopes. Then dissimilar elements also were placed together in A and B groups, and there was no certainty how many elements will be discovered between the two known elements, because atomic mass does not increase regularly. So these all were the limitations. That is why scientists looked forward for another criterion for the classification. Later on, Moseley shows that atomic number is more fundamental property of an element, that is the number of the protons present in the nucleus of an atom. So the basis of classification was changed to atomic number. Then elements were arranged in the increasing order of their atomic number. Again it was observed that there was periodicity in the properties. At regular interval, the elements with the similar chemical properties occur. On the basis of this, modern periodic law was given, which says that the properties of elements are the periodic function of their atomic number. This is a look of modern periodic table. Here you can see that there are 18 vertical columns of the groups and there are 7 horizontal rows. Now the first and second group are called the S block elements, because filling of electrons takes place in the S subshell. Then from 13 to 18 they are called P block elements. Then the groups which are in between the two, that is from 3 to 12, they are D block elements. And then at the base you can see there are 2 rows. Actually these two, the elements which are placed in the 2 rows, they are the part of this periodic table. The first one is of you can see of lanthanides. Actually you can see the pink box in the 6th period in the 3rd group. So actually the 14 elements which are placed in the first row, they all have properties similar to lanthanum. So they are in that one box and they are called the lanthanides. Then the bottom row, that is of the actinoids, and actually they are having the properties similar to actinium, which is in the 7th period, again in the 3rd group. So these are called actinoids. So this way all the known elements, they were just placed in a table. The elements having the similar chemical properties were placed in the same group, and having dissimilar properties were in the different groups. Here the modern periodic table, as I said, it had 18 groups and 7 periods, and elements that contain the same number of the valence electrons, they are placed in the same group. So, and we know the chemical properties of an element depends on the number of valence electrons, as the number of valence electrons in the elements which are placed in the same group is same. So they show similar chemical properties. And in the different groups, as we go across the period, you will see from left to right as we go, the number of valence electron keeps on increasing by 1. So as they are having the different number of valence electrons, so elements of the same period, that is the horizontal row, they have different chemical properties because they have the different valence electrons. Now, here one more advantage of this modern periodic table was, as now the position of elements can be related with the its electronic configuration. As if I just take one example, let it be sodium. Sodium is Na, its atomic number is 11. If I write its electronic configuration, it is 2H1. Now, if I see the valence electron, it is 1. So, the number of valence electron tells us the number of group. So, it belongs to first group. And total how many shells it has? It has 3 shells. So, number of shells tells us about the number of periods. So, it belongs to the third period, first group of third period. So, this way, when the basis of classification was changed from atomic mass to atomic number, we could relate the position of element with its electronic configuration. We could give the explanation ki why do elements in the same group have similar chemical properties, whereas the elements in the different groups have dissimilar chemical properties. Now, the merits of long form of periodic table, as I said, it is based on more fundamental property of element, that is atomic number. Atomic number of element always remains same. In isotopes also, number of protons will always be same. Number of neutrons may vary, but number of protons, that is atomic number, that always remains same. All atoms of one element will have same number of protons, same atomic number. As I said, the other one is the position of element could be related to the electronic configuration of an atom, and here you can see that there was separation in the elements. On the left hand side, and the central part was occupied by the metals. Right side of the periodic table is occupied by non-metals, and then there is a zigzag line which separates metals and non-metals, that is by the metalloids, which have some properties of metals and some of non-metals. So, separation of elements was also done correctly. Now, there were again some limitations in modern periodic table. One is again the position of hydrogen is not certain. It can be placed in first group with the alkali metal having the 1 valence electron in its electronic configuration in its first shell. Another, it can again be placed in 17th group, these halogens, which are halogens, they have 7 valence electrons in their valence shell. So, they are one short of the complete octet. Same with hydrogen also, as it has only 1 valence electron, and the maximum number of the electrons in the first shell can be 2. So, it is short of 1 valence electron. So, its electronic configuration resembles with alkali metal as well as with the halogens. So, again position of hydrogen is not certain. Now, configuration of helium. Helium is atomic number is 2. So, if we go by this law, the number of valence electrons will be telling us the group, then it should belong to second group, but it is placed with noble gases in 18th group. Reason being, it has 2 valence electrons, and we know first shell cannot have more than 2 valence electrons. So, it is complete. So, that is why it has been placed with noble gases. And it is again lanthanides and actinoids. They were placed separately. So, there was no place in the main body of the periodic table for lanthanide and actinide. So, these are some limitations of modern periodic table. Now, how do different properties vary in the modern periodic table when we go across a period and when we go down in a group? So, let us first discuss the atomic size. That atomic size is always described in terms of atomic radius. That is the distance between the center of the nucleus and the outermost shell. Right. So, when we go across the period, you know, number of valence electrons goes on increasing. Right. So, they and the electrons, they are in the same shell. So their distance remains the same, but the number of protons also in the nucleus will be increasing. As a result, the nuclear pull goes on increasing, so that pulls the number of protons. They pull the valence electron closer to the nucleus. As a result, the atomic radius or the size of the atom decreases as we move across the period. If we talk about how does it vary in a group. So in a group, as we go down at every, from first, in first group if we consider, then from first period if we go to the second one shell is added. Again at every step one more shell is added. So the size goes on increasing, the distance between the center of the nucleus and the outermost shell goes on increasing, the size increases as we go down in a group. Now valency, that is the combining capacity of an element. So what happens, it again, valency is a number of electrons which an atom either loses, gains or shares to complete its valence shell. So first the valency, it increases from first 1 to 4 and then it decreases to 0. I am talking about the normal elements only, the elements of S block and the P block. Then down in a group, the valency, as the number of valence electron in the outermost shell remains the same. So valency remains same in a group. Now metallic and non-metallic character. Metallic character is that the property of an element, how easily it loses electron, the valence electrons. Non-metallic character, how easily it gains the electron. So metallic character, as we go from left to right in a period, so again the nuclear pull goes on increasing, so the tendency to lose electron, that is metallic character, decreases, and tendency to gain electron increases, or the non-metallic character increases. If you just talk about the groups, if we talk about the groups which consist of metals, so you will see the size goes on increasing or nuclear pull on the valence electron goes on decreasing. So easily elements lose electron as we go down in a group. So metallic character increases when we down in a group. And again, if we just consider group 16, 17, then you will see that these are the groups in which non-metals are placed. Again, the electronic, nuclear attraction goes on decreasing, so there will be less attraction for the incoming electron, or the non-metallic character will go on decreasing. So with this we have completed the chapter. Let us summarize. One, as I told you, that we are studying about the periodic classification, in which we have studied about Dobereiner triads, Newland's octave, Manliffe classification, modern periodic table. Then we studied about the trends in modern periodic table, that is atomic size, valency, metallic and non-metallic character, and then the nature of oxides. Oxides of metals are mostly basic or amphoteric in nature, whereas the oxides of non-metals, they are mostly acidic or they may be neutral in nature. Thank you, children.